This 47-74 lecture, it's a starting lecture for the section 3 for analyzing the text data or the 1D sequential data, because in this section we will talk like Bayes model, Bayesian classifier, and there's a lot of probability proportion there. So this is the slides to students who need a little bit review about probability. And most of the lecture here are the recordings from my last year. All right, so let's get started. So first I will talk about big pictures, then I will split the whole video into two parts. The first part is about random variable, and the second part is about these three important probability calculation: joint probability, marginal, and conditional, and how do you calculate it. And the third module will be a concrete example. How do you apply those rules to calculate interesting like a joint probability or marginal probability or conditional probability. All right, so
so the bigger pictures. So what is probability? In one sentence, it's just those type of model trying to see how data are generated. It's from model to the data, and the other way is from the data to the model. It's a procedure normally called estimation, learning, or statistics. So this is the bigger picture, how your position of all those concepts you normally learn. And actually inference or prediction is also from model to data or prediction. So when we normally see, we have a machine learning model, and we're trying to predict something. So it's not observed data, but it's just when you have a model, you try to predict on the new data. So to the data. So model to data is the data generation process. Data to model is the model estimation or model learning, or estimating statistics or moments from the data. And probability, I'm going to skip all those. You should read by yourself, and these are the important concepts that you should know about probability. So just to about probability, like accounting basics, discrete versus continuous, and tail bounds or central limit theorem. Maybe this is a little bit too much, but I guess maybe some of you already learned this in your probability course before. Statistics normally cover MRE, Bayesian estimation, hypothesis testing, or those kind of regression model actually covered in the beginning of this course belongs to the statistic, and you can even think machine learning is part of the statistic from this perspective, because we are trying to estimate the model from the data. Okay, probability. So there are different views. There are frequentist view or uncertain Bayesian views. So most likely what you learn, it's about if you can count, what's the ratio of the event happening versus the full. So, but for some events you cannot count. It's based on domain knowledge. So you can think about it's more a measure of uncertainty. So I'm going to skip very quickly. So the whole event, the whole sample space is maybe 1, and if you your specific event happening is the area can be represented as the area over the full. You can think about probability as a measure of uncertainty. It's measuring how certain a specific event taking place. So in this one, it's more like the area of the red boxes. If you're throwing a die, and how likely my die hit the head. This is the region that die going to hit, and this is all the regions that your die will be likely to reach. And then event space. So event space is the set of all the outcomes that, for example, when you throw in the die, there are 6 outcomes, 1, 2, 3, 4, 5, 6, it's the event space. And the specific element there is called elementary event. And a specific event is a subset of the sample space. For example, in the throw in the die, 1 to 6. So what is an event? What is the even event? In fact, even event is a subset including 2, 4, 6, right? Because it's an even number from the throw in the die. Then the P even it's 1/2. So assuming every phase has uniform probability, you're throwing the die. So again, just the concept, sample space, it's a set of all the outcomes. Event space, event, it's a subset of a sample space, and the event space is the set of all the possible events. So in the event space, it can include the empty event or the O event, which includes all the possible elementary events. It includes all that sample space O. So yeah. And what's the probability? Probability is a definition over the pair of that sample space and event space. And it's just every event has a probability, and the event is a subset of the sample space. That makes this axiom, right? The probability is bounded from 0 to 1. And if 2 events are disjoint and their union probability is a summation of first event plus the second event. So this is just trying to show you probability is always 0 to 1 from the impossible, which is the empty set, to certain with the sample space, and things in the middle are unlikely to likely, or there's even chance in the middle. And the other is this extension of the disjoint decomposition. Your sample space can normally be decomposed into this the union of the multiple disjoint events. Then the probability of that sample space O, it's a summation of all this together, which is what? So what is PO? O is the sample space. What is the probability of sample space? 1. This is all pretty elementary. I hope it's this kind of retrieve your memory from your undergrad probability course. And then, this is if the A and B2 event, remember events are subsets, right? In the end, it's about 2 sets operations. Everything here is set operation because event is a subset of sample space. So if A and B2 subsets, they are not disjoint, they have overlap region, intercept regions, then their union is PA plus PB minus PA and B. So this is the most basic OR operation for probability. And then it's also extending to the NOT operation for probability, right? P not A is because A and not A are disjoint events, and their summation is O, it's sample space. So that's why P not A is equivalent to 1 minus PA. Very, very basic. And then the other important is called the law of total probability. So we actually can normally decompose or represent A event as a summation of A and intersection with B plus A intersect with not B. So this is really application of the NOT operation plus the disjoint operation. You can even derive this. So remember that this is a very important important rule we always use later. You can actually prove it. I think I proved it here. And then, so sample space, event, and event space. And then what is a random variable? So we always talk about random variable, right? So what is random variable? In fact, random variable is just a function. Each random variable is a function mapped from the sample space to an attribute output T. This is a very important concept. So for example, my sample space is all the possible students in my class, and then I want to represent what is the subset hardworking students. So P hardworking equals to yes are the subset who works hard. So this is an event, right? But I actually can just represent it as a function H applied to all the students, and then if it's equals to yes, those are the students that works hard. So it's a function. It's a function map each elementary event to an attribute output. For example, H is a random variable. You apply that random variable, then you essentially split your sample space into yes or no. And that's exactly pH, how it represented, like pH equals to yes, or pH equals to no, and H is a random variable. So this is one kind. There's other kind like P grade, the grade of all the class in this, all my students in this class can be grade A, or grade A plus, or grade B. So that's the other way to split my sample space through this function. It's a grade function. So in the end, random variable is a function on the sample space. It maps the elementary event in the sample space into some output attribute set. And that attribute set, the output is exactly the random variable's values. So pH equals to yes, or pH equals to no, pG equal to A, pG equal to B, or pG equal to A plus. So, question about this, because we always talk about random variable, right? So what is a random variable? And remember that it's a function on the elements of the sample space. All right. So, and there are a lot of different notation to represent random variables, and we normally use uppercase letters or names for random variable, or lowercase letter to represent the values of the random variable, right? So what is random variable? It matches this elementary event into attribute sets, and the values of that output attribute set is the random variables, the value. So for example, gender equal to male, or gender equal to female, it's one random variable, or a major, so what's your major, it's another random variable, or a grade is a random variable, or height, it's a third, it's also a random variable. It's a function applied to that elementary event. All right, so in general, we have either discrete random variable or a continuous random variable. So the thing is decided by that output attribute set. If that attribute set is discrete, and that's discrete random variable. If the output attribute set attributes its continuous values, it makes a continuous random variable. So if X is a random variable, it can only take exact exact one of the value from this. You can think about this in a vocabulary or a dictionary. So so this is really just apply everything we learned before, the OR operation, and a NOT operation, and the total summation operation on this random variable created event space. So everything we had before, those are properties on the event space, And random variable is just a function project elementary to the subset. That's why everything you learned in the event space, those axon, those properties, all can be applied on the random variable too, because that fundamental relationship, functional mapping relationship. All right, so if your random variable can take x1 to x4 different values, because as I said, it can only take exact one of value in the discrete variable space, right? Which is equivalent to using my random variable value output, I can decompose my sample space O into 4, if assuming x1 to 4 are the possible output, possible value for random variable x. It's equivalent to, I can use that value to decompose this the sample space into 4 disjoint subspace. So that's why the summation of px, summation of I from 1 to, assuming it's 4, or in this case, p, use capital P, x equals to xi equals to what? 1. The same thing, the same trick I asked you before. So this is also so this looks like so simple, but you can use this to do a lot of other probability, to prove many other lemma or conjectures later. So what is the typical discrete random variable, for example, Bernoulli or binomial, as I asked you? So this is 2 different scenario. You're flipping the coin. So you flip a coin, the head probability, assuming it's p equal to 0.5, or you're flipping a coin for k times, for example, 100 times. So what type of probability distribution I use to describe this case? What type of probability model I use to describe this case? So the upper one is, which model should I use to represent flip a coin? Bernoulli distribution. And what's the lower case? You're flipping a coin for k times. And that's binomial distribution. So flipping a coin, the generated event space is what? So the value is, there are only 2 outcomes now, right? So again, random variable is to project into a attribute output space. And the most important is what are that output attributes. So flipping a coin, there's only 2 cases output, head or tail. And this is my value, h and t. And what I need to care is just h and t. However, for this lower case, it's about flipping the coin k times. And you have to know the k times. And this represents the number of, what you need to care is the number of heads over the k times. So this is the Bernoulli distribution normally used to represent this, and the upper is it's representing a binomial binary random variable, and the lower represent an integer random variable. So the upper is a binary, and the lower is integer. So which I'm trying to represent is this number, p number of heads. And the outcome is 1, 2, until k. And here I only care about head or tail. There are only 2 cases. Okay. I hope this is clear to clarify what's binomial Bernoulli distribution are representing and what's the binomial distribution are representing. All right, this is only really basic and should already be covered in your probability entry course. yeah, so yeah, this is the I'm trying to see the binomial, and then there's some kind of format issue here. It's supposed to be like this. So there are also other type of probability kind of popular one is a uniform distribution. You have maybe n different outcomes. They are equivalent, all equally likely, which makes each one of them is 1/n probability. And for the binomial distribution, the probability distribution normally like this because the number of heads, right? So you flipped k times, what's the probability I times are positive, are ahead? So you flip k times, and then there are I of those ahead. I heads out of k, so it just k pick I, because the probability of head is p, so it's the p to the, because there I times is head, so this is p to the power of I, and the other is tail. The tail probability is 1 minus p, your k minus I times is tail. So this gives you that probability of I heads out of k, throwing it, not throwing it, actually flip the coin here. All right.